Relax the bridges.
Assalamualaikum warahmatullahi wabarakatuh. Selamat sejahtera. Can you hear me?
Yes, Doctor.
Okay, so today we continue our lecture at the slide number 30. Okay. So last week I discussed with you already circuit 1.1 and I think circuit 2. Okay, so let us revise again. Okay, you are given a CR circuit, okay, where you have to required to derive the mathematical model, which is V out over V in, okay, to see the relationships between the output and the input. So we simply model it using Kirchhoff voltage law, and then add the V in, okay, the loop number 1, and then Ohm's law at the output, okay, and then we take the Laplace transform for VI, and then the V out as well. Then we know that I is equal to V naught over R. Then we replace it with inside the I current, okay, the integration of I we replace with IS, and then we get between the VI and V naught, and then we get tau S over 1 plus tau S, where tau is equal to RC, and it's known as time constant, okay? Then we change the positions of the R become C, and C become R. So like this, and we want to investigate whether it gives the same mathematical model, right? So again, at the loop 1, we derive the input Kirchhoff voltage law, VI is equal to VR plus V naught, and V naught now is not resistant, it's capacitance, so V naught now is 1 over C integration I dt. So we're taking a Laplace transform for both V naught and VI, okay? So we get the VI and V naught in the Laplace transform by assuming a 0 initial conditions. Then we eliminate the current, okay, from the equation VI and V naught. Then we will obtain 1 over 1 plus SRC. RC is equals to tau, so it becomes 1 over 1 plus tau S, where again tau is the time constant. Now we move to circuit number 2, where you are given 2 resistance and 1 capacitance, okay? And we have input and output as V in and V out. And again, now we use the same concept as RC previously in circuit 1, okay? So we will obtain VI IR1 plus V naught, okay? But now V naught have 2 elements, which is R2 and capacitance, okay? So now we have to take a Laplace transform for VI and V naught, okay, together. So we will obtain VIS equal to I R1 plus V naught, okay? And then V naught is equal to R2IS plus I over CS, because I over CS is the capacitance part, okay? Then we rewrite again by factoring this IS, okay? This IS and this IS we factorize. Then we will obtain IS is equal to V naught CS over R CS plus 1. And then we bring the, we use this I inside these equations. Okay, so we will obtain V0 over Vi, R2 CS plus 1 over plus R2. Shafiq, please off your microphone. Muhammad Shafiq. Muhammad Shafiq, please off your microphone. Okay, thank you. So we obtain the V0 over Vi, R2 CS plus 1 over R1 plus R2 multiplied by CS plus 1. So that is the transfer function for circuit number 2. Okay, so this one is directly, okay, is another method directly without using the time domain. Okay, this one we are using time domain. We take Laplace transform, so 2 steps. But in the slide 37, we don't have to use the time domain. We straight away using a Laplace transform also can. Okay, also can. It's much faster compared to the previous one. Circuit number 3. Nabil, off your microphone. Thank you. So for circuit number 3, we have 2 loops, which is this one, L1 and L2. Okay, loop 1 and loop number 2. Or can simply write it as loop 1 and loop 2. Okay, where you have 1, 2, 3, 4 components on board. Okay, now V0 is the voltage drop between L2 plus R2. Okay, and C2 as well. So as usual, you're using a Kirchhoff voltage law in time domain. Okay, so Vi is equal to I R1. So you have to be very careful on this part because you have a current here, which is IR1. So you label it as IR1. And this current is IC2 that flow through the capacitance C2. And then this current, okay, you can see which is IL2. Okay, so IL2 and IR2 is the same, so we use just one notation, which is IL2. Okay, so Kirchhoff voltage law, this loop number 1. Okay, this one, loop 1, which is Vi is equal to IR1 R1, yeah, and V0. Okay, but V0 have 2 expressions. One is for C voltage drop at VC2, and the other one is VL2 plus VR2. That's why you see here, you have equation 2. Okay, V0 is equal to 1 over C2 integration IC2 for the voltage drop at capacitance C2, which is equal to voltage drop at L2 inductance and resistance R2. Okay, that equation number 2. Then you apply Kirchhoff current law. Okay, so Kirchhoff current law is at the node here, this node. Okay, there is one current entering this node and 2 current exit from the same node. Okay, which is IR1, this part, IC2, this part, and IL2, this part. Okay. So 1, 2, 3 is in time domain. Then you apply Laplace transform for equation 1, equation 2, and equation 3, respectively. Then you will get equation number 4. Okay. Equation number 4. Then equation number 5. Okay, which is Laplace transform equation 2. And equation number 6, which is Laplace transform of equation number 3. Okay, so you manipulate the equations. So try to get V0 over Vi based on the 6 equations listed on the left. So you will get the transfer functions, okay, which is shown in the slide number 38. Okay. Or if you don't want using the time domain directly, using the Laplace transform straight away, also can, and you will get the same answer as slide number 39. Okay. So these are another steps as well. Okay. For slide number 40 is the same thing. Okay. It's the same thing, it's a continuation, so 39, and you will get the same answers as well. So the more loop of the circuits, the more complex the transfer functions, okay? So you're given another circuit, which is circuit number 4. Determine the transfer function for the circuit shown in below by assuming no external load. Okay, so you have a Vi over there, okay, as the voltage input, and you have the resistance, okay, as the VR is as the output, okay, of the systems. So find the transfer functions, which is V0 over Vi in S domain, okay, to show the relationships between the output and input. So by applying Kirchhoff voltage law to the circuit, KVL, okay, here, Vi is equal to voltage drop at inductance and voltage drop at the resistance parallel with the capacitance, okay. So you can see here, V0, Vi is equal to L, dIL dt. This is for the inductance, plus V0. But V0 is equal to Ohm's law, IR, multiplied by R, and at the same time is parallel with the capacitance, 1 over C IC dt, okay? So again, these two equations, Vi and V0, we apply Laplace transform, okay, both sides. Sorry.
It's all good.
So Vi is equal to Ls, okay, ILs plus V0, and then V0S is equal to IRS equal to IC over SC, okay, after we take the Laplace transform. Then we know that at this node, okay, there is a Kirchhoff current law over there. Kirchhoff current law, right? So this is the main current, which is IL. This is the IC, okay, part of IL. And this is IR, part of IL, the main current. So we can see that it is the total of IR plus IC, okay, for the inductance current. So you take a Laplace transform, IL equal to IR plus IC in the S domain. Then you know that IR is the Ohm's law, so V0 over R. Then the capacitance, when we apply Laplace transform, it becomes 1 SC V0 S. Okay. See, this is a Laplace transform for current flow in capacitance. Okay. Kalau the voltage, I over CS. Kalau the current is V multiplied by CS. Then rearrange the equations, okay? VI minus V0, which is equal to LSIL. S. This one is from the main equations. Then VI is equal to V0 is equal to LSILS. Insert this IL inside the equations. Okay. Then factorize the V0 common factor, which is this one, and this one. Okay. So you factorize, then the rest will go into in the bracket, which is 1 plus LS over R plus LS square C. Okay. Then we get the V0 over VI. We rearrange the equations. Then it becomes LCS square L over RS plus 1. In fact, you have to simplify, so make it better, like this, 1 over LC S square. So this one will become 1 over RC S plus 1 over LC. Okay, so the final answer for these examples. Okay, any questions? Abdul Rahman Ludin, any questions? Abdul Rahman Ludin, absent. Ahmad Zulbiri, any question? Tak datang. Aisyah Akram, any question?
Yes, Prof. So far,
question?
no. Cuma a bit, but I just impressed the background. The background. I thought it is the real.
Ada pun tak nampak pun? You nampak ke?
Yes. I thought it's the real. I thought that behind you is the real human. But when I keep seeing it's only the virtual. Pardon me.
I have question for you.
Yes, bro.
Because I cannot see anybody behind me. So I think maybe you not enough sleep maybe. Okay, so my question is, what is the Laplace transform for current flow in the capacitance?
Laplace, what?
What is the Laplace transform for current that flow in the capacitance?
That flow in capacitance. Capacitance. Transfer function for capacitance. I over no.
It's very simple. What is the Laplace transform for current that flow?
Oh yeah. IS equal to CSVS. VS in terms of transfer function.
VCS lah.
Yes, correct. Sorry. I'm complicated.
Amir Farhan.
Yes, Prof.
Any question?
So far, so good, Prof.
Okay, I have a question for you.
Okay.
What is the Laplace transform for voltage drop at the capacitance?
LC S squared plus L over RS plus 1.
Salah. I'm afraid your answer is wrong. Amir Farhan. Is Amir Farhan pula. Maisara.
Yes, Prof.
Same question. What is the Laplace transform for voltage at the capacitance?
I over CS.
Huh?
I over CS.
I over CS. Yeah, betul. I over CS. Very good. Calchas, New Ing. Calchas? Tak datang. Isma, is that? Isma, what is the Laplace transform for voltage and inductance?
Voltage and inductance. I inductance. Tak tahu tak.
Tak tahu. Cek balik lah. Tak faham lagi itu. Muhammad Afzal.
Yes, sir.
Same question. What is the Laplace transform for voltage and inductance?
LSI.
LS. Bagus. Muhammad Akmal Hussain. Akmal Hussain. Tak datang. Farhan Rushdi. Farhan Rushdi. Tak datang. Hazim Shukri. Hazim Shukri.
Yes, Doctor.
What is the Laplace transform for current that flow in the inductance? Tak tahu. Okay. Nur Najwa, Abdul Halim.
Yes, doctor.
Same question. What is the Laplace transform for current that flow in the inductance?
V over LS.
V over LS. Okay, thank you very much. Okay. Right, so we continue with the next one, which is the RL circuit. Okay, so RL circuit also important in electrical and electronics. Okay, so we see how we derive for Kirchhoff voltage law at the loop number 1 here. Okay, so you can see that apa ni? You punya input, voltage input is equal to, I better share dengan ni lah, pakai iPad. Nampak tak?
Apa?
Lapar?
Nampak, Prof.
Oh, lapar. Baru pukul 11. Lapar. Okay, RL. So this is your input and this is your output. Okay. Right. So as usual, kita pakai KVL kat dalam ni, loop number 1. Okay. Loop number 1, which is VI equal to VR plus V0. Okay. But V0 adalah voltage drop at inductance, which is over here. Right. So VI is equal to IR plus V0. Okay. Then we rearrange the current. Okay, I is equal to Vi minus V naught over R. And then V naught else d per dt, so we replace the I, okay, the current that flow in the inductance with these expressions. Then we apply Laplace transform, then we obtain the transfer function, which is Ls over R plus Ls. And then we change, instead of here, we change resistance and then inductance. Okay, we change the place and we derive again. Okay, using the same concept, then we obtain the transfer function is R over R plus Ls. Okay, R over L plus Ls, which is different from here. This is RL, okay, and this is LR. So itu adalah sebagai apa orang cakap contoh. Okay, I will give you more examples. Okay, more examples in the tutorial and preparing the tutorial. I will give you inshallah after finish chapter 2. Okay, modeling of mechanical system. So mechanical system in this chapter 2.3 will consist of translational, rotational, and rotational with gears. Okay, so mechanical system here, okay, is using a Newton's law of motions. Okay, Newton's law of motions, which is the first law, the velocity of a body, okay, remain constant unless the body is acted upon by external force. Okay. And then the second law is the accelerations of a body, which is A, is parallel and directly proportional to the net force, which is F, and inversely proportional to the mass, which is M. So that's why F is equal to ME. And then the third law is the mutual forces of actions and reactions between the two bodies are equal, opposite, and collinear. Okay, so in order to do that, we must understand the concept of Newton's law of motions. Okay, in terms of velocity, acceleration, and mutual force of actions and reactions. So this is the table, okay, for spring, for viscous damper, and for mass. So spring, damper, and mass applied in many our daily life, okay. For example, Nurul Hidayah, can you give examples where we can see spring, damper, and mass in our daily life, in our systems, daily life?
Spring. Give the example for the component.
Okay, Sarah, combination pun boleh. Better combination. Mungkin mass dengan spring, mungkin mass dengan damper, atau ketiga-tiganya. Tak tahu, tak apa. Nurul Nabila? Tak datang?
Ya, Doktor.
Tak menyaut. Kalau tak menyaut, tak datang. Nurul Nabila, kat mana? Where we can see application of mass, spring, and damper.
Kalau pijagari tak
Pijagari? Astagfirullahaladzim. Oh, ada vaksinnya. Sakari Ahmed. Sakari. Share. Where we apply mass, spring, and damper in our daily life?
For spring, we use cars under below the tire.
Oh, you mean suspension system?
Yeah, that's
Okay, suspension system, car suspension system. So if you see a car, you have 4 wheels, 2 at the front and 2 at the rear. So if you look down near the tire, you can see there is a spring and damper, okay, attached to the mass. Mass is the car body, okay?
Yeah.
So that is the examples. Any more? Sharifa Khairunisa?
Yeah, Doctor.
Kat mana kita apply mass, spring and damper?
I'm not sure, Doctor.
Nur Syuhada? Siti?
Saya, Doktor.
Ya, saya. Kat mana? We apply?
Yang buai bayi tu.
Buai bayi. Apa nama tu? Buai laju-laju.
Bukan tak yang enjut baby dalam buaian tu.
Sakari tak faham. So tak payahlah jawab.
Google.
Baby cradle, Doctor.
Baby cradle. Okay lah. Baby cradle also can. Okay. So this is the equations. Okay. F is equal to Kx. X is the displacement. The force is equal to Fv, which is the friction, dx over dt. And F is equal to m, d square x dt square. X is the displacement. So when we apply Laplace, okay, so it will give you K. This one similar like a resistance. And FBS, okay, FBS for the damper, and ms square for the mass. Okay, V is velocity. Okay, V is velocity. So this is the system, okay. For example, we have a mass here, okay. And we have a force towards the right, okay. And we have a displacement, xt, okay. Displacement is anjakan, right? Then we have a spring with the spring constant K. And we have a Fv. Fv is the constant of the damper in the liquid. Okay? The liquid inside the damper. We call it as the damper constant. Okay, and mass in kilogram. Okay. So we apply force, F of t points to the right. Okay. Then mass is traveling toward the right. Okay, below the travel, when it travel, so it will give you a new position with the new displacement. All other forces impede the motions and act to opposite directions. Okay, so this is what I call a single input and single output system. The input is Ft, okay, and the output is the displacement. So you can see here the mass, okay, F is equal to ma, or is equal to d square x dt square. Okay, and then I forgot to write m here. Okay, it's m. The m, please insert m inside your notes. And then the dashpot or the damper with reference, okay, where you have a F, the force is equal to FB, which is equal to B dx per dt. So B is the liquid constant inside the damper. Okay. Oh, kita panggil dia sebagai viscosity. Viscosity. Okay, dalam bahasa in Malay we call it as viscosity. Kekenyalan. Okay.
Kental, dokter.
Kental. Lagi halus kental minyak itu lagi mahal harganya. And then dashpot or damper without references. So if there is no references, so we have to find what you call that, the difference between x1 and x2. Okay, so give a force here, then create x1 and x2. So the difference will be F is equal to B per dt x1 minus x2. And then the springs, as usual, F is equal to Kx. So K is the spring constant. So every item in mesh, spring, and damper have their own age. The more aging the items, so it cannot maintain the constant of K and B, okay, of the spring constant and of the viscosity because of the aging factor. That's why when you drive a car, old car with 10 years or 15 years suspension system, you will not feel soft anymore. It will become hard, okay, and it's not comfortable when the car hit the bump or hit the hole on the road. And then spring without reference, same to the damper as well, which is F K x1 minus x2. With and without reference. Okay, yang ini ada reference. Okay. This is the reference, right? Same this one, ada reference. And this one without reference. So you have two displacement, x1 and x2. Okay, so similar to these examples just now, okay, you have these connections of spring, damper, and mesh. So what we do first is we draw the, what you call that as a free body diagram. Okay, so this is what I call as the free body diagram. Okay, so from the free body diagram, we indicate all the forces and the directions. For example, this is the force on the system, okay, which is on the right, and the displacement is on the right direction as well, okay, and the opposite force that will bring back the mass to its original positions is kxt for spring, fv x dot, and m x double dot, okay. So usually I call it as x dot, which is dx per dt, and this one is x double dot. So x double dot stands for d square x dt square. So the equation of motions, okay, the force equations, this is what I call as the force equations. So this one is 3 force on the left. The total is equal to the input f of t. Okay, then we apply Laplace transform. Okay, so when we apply Laplace transform, this mass will become ms squared xs plus fv xss for damper and kxs for the spring. Okay, so this one in time domain and this one in s domain. Both are the same. Depends on you. If you want to write this one, you need to transform to this one, or you can simply directly, okay, draw like this, and you get the equations. So the transfer function is x over m, x over f, okay, X over F over F is equal to 1 over M over S square plus FV over M S plus K over M. Okay, so is a second order system. Okay, this system is known as a second order system because the denominator of the transfer function is the highest order is 2. Okay, we have another examples here. Okay, for you to think about it. The external force Ft is the input to the system and the displacement Yt of the mass is the output. Okay, the displacement Y is measured from the equilibrium positions in the absence of external force. Find Y over F. Okay, find Y over F. Assume that the system is linear and all initial conditions equal to 0. So I just give you the equations here for you to derive. Okay, it's very straightforward. Okay, draw the free body diagram, then get the force equation, Laplace, and then you can get the transfer function Y over Fs. Ihsan Aulia Rahman, can you off your microphone? Ihsan, microphone off. Right, then find the transfer function is x2 over f, right? x2 over f for these systems, so which have a 2 mass, okay, 3 springs and 1 damper. Okay, so this is from the normalized book. Okay, from the normalized book, you can refer to the book chapter that I give to you in the WhatsApp list. Okay, so in order to solve this, we have to draw the 2 free body diagrams, which is correspond to M1 and correspond to M2. Okay, so in this case, we just wrote here, force on M1 due to motion of M1, okay, is shown on the left, and force on M1 due to the motion of M2 is shown on the B, okay. So then it sum up, total up between M1, okay, between M1 here, as shown here, okay, and then you get the force equations, okay, according to the arrow. You can see that 3 arrow on the right and 3 arrow on the left, okay. And then for M2, force on M2 due only to the motion of M2, and then force on M2 due to the motion of M1. Okay, so sum together, and then you produce the force equations. Okay, so 3 force on the left and 2 force on the right. So you get the second force equations, and from there you can solve it. Okay, for x2 over f or x1 over f. Okay, by creating matrices. Okay, for further reference, you can refer to the book chapter of normalized that I sent to you. So we see another. Sorry.
I have a question.
Yep, Afika.
For the previous slide, the equation for the force going left and right, is it will be any different if we use different sign, like negative sign and positive sign, like we make it the negative, make it positive.
Which one? A slide number?
Next slide.
This one.
Is it? Yes, this one.
Okay.
Here we notate that if it is going right, we put it as negative. But what if we make it positive? Will it be the same?
You mean the X or the F?
The long
Force or
equation just
displacement?
now.
Huh?
The long equation just now. Maybe
Or the
next
long
slide.
equation, this one?
Yeah, this one. Yeah.
Okay. Okay. What's wrong with these equations?
Will it be the same if we change the sign? Like
Dia negatif ni sebab daripada from right to the left. That's why they change to negative.
okay.
Previously was on the right.
Okay.
See? Kan dia ada dua ni, K2, X2, FV, SX2 kan, plus F.
Yes.
So when you left Fs alone on the right and you bring this one to the left, that's why it become negative.
Okay. Thank you, Doctor.
Kita tak sarapan lagi.
Excuse me, Doctor.
Yes.
Okay, before you leave this page,
name?
As my name is Zakaria.
Zakari.
Yeah, I have a question about this diagram, M1.
M1.
Yes. Actually, as you can see, we have two forward forces, right?
We have two mass, M1 and M2.
Yeah.
And we have two displacement, X1 and X2.
Yeah, two displacement.
But we still have one force, Fs.
Okay, so is there any force that dragging back this body to the back?
No, because you read the sentence here, force on M1 due only to the motion of M1 when M1 is moved. And M2 we assume not moved. Then force on M1 due only to the motion of M2. See?
Okay, so M2 will not move.
Yeah. If you don't assume, so it's very difficult to create the force equation from the free body diagram. That's why you must draw the free body diagram as shown here, M1 and for due to motion of M1, M1 due to the motion of M2, and then M2 due to the motion of M2 and M2 due to the motion of M1. Okay, so once you get this, so you have X1 and X2, and the previous one, X1 and X2, so you can create the matrices. Okay, so I don't show here, but it's written in the book chapter, you can refer. Right, so this is, sorry. Okay. So next example in slide, which is slide number 62. So now the example is different. So we give straight away the value. Okay. For example, for damper 4 Newton second per meter, that is the unit for the damper. Mass is 5 kilogram. And inductance is 5 Newton per meter. Okay. Again, one force, one displacement, and one mass. So in this case, you just M is equal to 5, K is equal to 5, and FV or B. So in this example, we use SFV is equal to 4. Okay, as shown here. Okay, so so we have to find the transfer function, which is x1 over fs. Okay, for a system shown in the figure, section 2.5. So we wrote equations. So you have x2 is supposed to have x2 over here. Okay, at the end of this. Okay. So is a typo error over there. right? So draw the free body diagram for 5 kilogram. And then you can see that there is a 3 force towards the left, okay, and 1 force towards the right, which is 5x2. Then this is the first equation of the force, and then the second equation, which is minus 5x1 plus 5x2 is equal to F. So adding the equations, so it become x1 over fs 1 over 5 over s plus 4 over 5. For the next examples, okay, which is here, okay, so in the book as well, so you have a 2 Newton meter with the displacement x1 and damper with the displacement of x2 and the mass with the displacement of x3, okay. So again, we produce the free body diagram, and then we produce the force equations. This is the equation that I told you before, which is the matrices, okay. So we have 3 by 3 matrices, okay, with x1, x2, and x3 for the displacement, and is equal to the force value Fs, okay, from these equations, okay. So in order to find x2, okay, so we have to use the Cramer's rule. Okay, you use the Cramer's rule, which is 5s squared plus 10, okay, Fs minus 10, okay, 0, okay, over 5s squared plus 10 minus 10 minus 10, 1 over 5s plus 10. So this is, we call it as a, what do you call? Determinant, okay? Determinant of the matrix. So you have to multiply, cross multiply, okay? This part and this part, by taking into considerations the main matrix here. Okay, so that's why you will get x2 over fs 1 over 10, 10s plus 7 over s 5s plus 1. You can apply this in the previous examples, which is here. This one, okay? So you have an x1 and an x2, and x1 and x2. So in order to find the x1 over f or x2 over f, you can use Cramer's rule, okay, to get the transfer function straight away. So I show you to here how to get the form x2 over f, okay, the details. Okay, so you can follow slide number 66 in order to get the answer x2 over f. Okay. So self-learning on the mechanical mass spring and damper by Ryan Douglas or Rick Hill is available in the YouTube. Okay, so you can follow as slide 67 by click the link as shown. So I stop here, then we will continue again the class on Wednesday at 2 p.m. Is it okay? Class at 2 p.m. Wednesday?
Okay, doctor.
Yes,
okay. So I see you on Wednesday.
Okay, Prof. Bukan cuti ke?
Yeah. Holiday on the Thursday lah. Okay.
Yeah.
Otherwise, it's very difficult to replace 2 hours.
Okay.
Yeah.
So still got class or not?
Online, class online.
Okay, no problem. Thank you, Prof.
Anybody celebrate Deepavali in the class? Anybody? Maisara, do you celebrate Deepavali?
No, Prof.
Huh? I don't see any Indian student here. We have 5 international, and the remaining is Malay students. Okay, I can say as is there any Go Ming? There's one Chinese over here. No Chinese, eh? Go, ada sini go. Ada kan? It's a Bumi Putra class. So we see you on Wednesday, 2 p.m. until 4, okay?
Okay, Prof.
Okay, thank you very much.
Thank you,
very
Prof.
much.
Thank you, Prof.
Thank you, Prof.
Thank you, Prof.
Thank you, Prof.
Bye.
Thank you, Prof.
Prof.
Thank you.